Okay, so for today, we're going to be talking about where do the EM waves reflect and what part of the atmosphere does that involve? All right, so if we draw a diagram of the Earth, and this is the atmosphere. Now, the ionosphere is the part of the atmosphere where the radio waves can reflect. So the ionosphere, now the word ion, what do you think is inside this part of the atmosphere? Ions. Now the reason being, let's just say that this is the sun. The sun will emit UV rays. So these are UV rays. And you might get cosmic radiation, cosmic rays. You might get gamma rays. So you get cosmic rays, you get gamma rays from space. And it would get absorbed in the ionosphere. For UV light, when it hits the atoms, it will ionize the atoms. So let's just say that this is the atom, you've got positive nucleus, you've got the electron, you have UV light. It hits the electron, and the electron will be ionized. Alright, so in the ionosphere, the radio waves can get reflected. So let's just say this radio wave is going this direction and it comes back. This is not to scale. So these are radio waves. These are low frequency radio waves. However, if you have high frequency, it can go through the ionosphere. So these are high frequency radio waves. And they can go through, so they can go through the atmosphere. And these can be for satellite usage, satellites. Low frequency radio waves, they will get reflected. Now these cosmic rays and gamma rays, they can get absorbed in the atmosphere. And what about these UV rays? Well, half will ionize these atoms, half will ionize, and half will just go straight through. So half will ionize the atoms in the ionosphere and half will just go straight through.
There are free ions and electrons in the ionosphere, in the upper atmosphere. The free electrons affect radio waves and radio communications, where the shortwave radio bands are reflected, enabling these radio communication signals to be heard over vast distances. Worldwide radio communications coverage is the result of this, although today satellites are widely used.
All right, so we're going to be talking about the electromagnetic spectrum and the rough guide on working out the wavelength. So the electromagnetic spectrum. And we're going to start off with the long wavelength and the short wavelength. Okay, so the one with the longer wavelength is the radio. Then it moves, then it gets shorter. It will be the microwaves. Then it's the infrared. then it's the visible, then it's the ultraviolet, then it's the X-rays, and then it's the gamma. Okay, so the radio waves, I remember it in terms of the powers. So the power is 0, and then it goes down by -2 each time. So -2, -4. We'll come back to infrared in a moment. This is -5, sorry, this is -6. This is -8, this is -10, and this is -12. Alright, so the infrared is actually, because it's quite close to visible, if you remember that this is actually -5, and the range of the radio is even to kilometers, so it goes to kilometers to centimeters. Now the microwave is 10 to the power of -2 meters. This is 10 to the -5 meters. Now visible, you have a range between 400, roughly 400 to 700 nanometers. And the one with the longer wavelength is the red. So actually they should be swapped, but this one is the red, and this one's quite close to blue. So here it will be 10 to the -8 meters, 10 to the -10, and 10 to the -12 meters. Alright, so there you have a rough guide of the wavelength of the electromagnetic spectrum. You start off with 0, it goes down by -2, apart from the infrared and the radio, because the radio has a very long range. The infrared is 10 to the -5, and the rest goes down by -2 each time. So this is the rough guide of the wavelength of the electromagnetic spectrum. Alright, so let's talk about how EM waves are transmitted through walls, for example. So let's just say that this is a wall. And these are the atoms. Alright, so let's just say that you've got gamma. Let's say that this is gamma, so this is gamma ray. And remember, it is 10 to the -12 meters. Alright, now what is the average size of an atom? Now the average size is 10 to the -10, isn't it? So 10 to the -10 is an atom. Now, the gamma ray, it's much smaller. So the gamma ray is smaller. So therefore gamma rays can pass through. Gamma rays can pass through. Now what about visible light and UV light? Now visible is about, what's it about? Well, 400 nanometers to around 700. Well, let's just say around, yeah, okay. So that is the range of visible light, roughly. And now, sometimes on the wall you will have paint, perhaps, paint. And so it's the interaction between the light and the surface. So usually it will get absorbed or reflected. So UV light or visible is around, well, visible UV is around 10 to the -8, isn't it? 10 to the -8. So what are the properties that make things go through objects? So here you have wavelength. Depending on the wavelength, it can also depend on how powerful that light is. So if it's powerful, or if it has a high intensity, Another one is the chemical composition of the structure. Also, you've got the actual physical structure. So you've got the chemical structure, you've got the physical structure. All right, so these are the four main ones, and the other one is also the thickness as well. Yes, the thickness of the material. So these are the factors. All right, so gamma rays can pass through. So gamma rays can pass through. Visible and UV light, they can get absorbed. It can be reflected. So that's visible and UV light. What about radio? Now radio is very long. So for radio, it can actually go through walls. So radio, it can be transmitted through walls. So if you look at the gamma rays, because it's so small, 10 to the minus 2 meters, the wavelength, and it can fit in between the atoms because it's very, very tiny, and so therefore it can pass through. However, for UV light, sometimes, depending on the structure of the atom, sometimes it gets absorbed by the atom, it can vibrate, and it can get reflected. So depending on the atomic structure of your wall, most UV light will be reflected. Yeah, because of the paint as well. For radio waves, because it has a very long wavelength, so it has a long wavelength. So because it has a long wavelength, and because it's also an electromagnetic wave, it is able to pass through the walls. Because compared to the radio wave, the wall is very, very small. So if you think about this is a wall, and the radio wave has a very long wavelength. So it is able to pass through compared to the wavelength of the radio. Because remember, what's the length of the radio? It's about centimeter to kilometers. So it is able to be transmitted through the walls because it has a long wavelength. This one has a short wavelength, so it can fit in between the atom. It is also energetic. This one is not that very energetic, but because the wavelength is very long, it is able to pass through. It is much longer than the actual wall, because the wall is usually very, very tiny compared to the wavelength of the radio. Now let's just quickly recap on the refraction part and using the equation V equals F lambda. Okay, so this is, let's just say that this is water and this is air. If you have a look at V equals F lambda, that's the equation. Now, if you remember that frequency stays the same. So frequency stays the same. Now, what happens to the wavelength? Now, the wavelength, because the speed of light is the quickest, so the speed of light is the fastest speed. Therefore, lambda must decrease for a denser material because it slows down. So F stays the same. So lambda must decrease And what does that imply? That implies that V must decrease. Okay, so that is the reason why the speed decreases. All right, we're going to be talking about alternating voltages and how that can produce an electromagnetic field, for example, a radio wave. So if we have an alternating potential difference, so alternating potential difference. Right, so potential difference could be where one side is positive and one side is negative. Now the electric field goes from positive to negative, so that's the electric field. That's the direction of the electric field. If you were to put a positive test charge, positive, it would go in this direction. So therefore the electric field is going in that direction. Alright, so the electric field here is going down. Now suppose you gradually make this be more negative and you gradually make this more positive. So what would happen if now you have minus, minus, minus and plus, plus, plus? What is the electric field now? So the electric field now would be going up. So let's keep doing this. So now the electric field is going up. So across here you've got a voltage. So here you've got a voltage across the plates. Okay, so what's the electric field here? The electric field is going down. And here what happens if that is negative, 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 positive, positive, positive. Now assuming that the maximum here is 3 volts. So here let's just say that this is 3 volts and then this is minus 3 volts, this is 3 volts. So what this is doing is that the electric field, let's just say that this is the strongest, going down, and then it's gradually getting weaker and weaker. 0, and then that's going up, up, and then again that's going down, and then that fits. So here you have alternating. So here this positive charge gradually gets weaker, becoming more and more negative, and then here you've got the maximum negative, maximum minus 3 volts. It just means that it's just swapped directions. And here, this gradually becomes more and more positive. Now, how does this happen? If you have, let's just say you've got a piece of wire, and you've got electrons going in that direction. So these are the electrons going in that direction. And then suddenly you change the potential difference, and now the electrons are going in this direction to the left. So what is the field here? Now if you were to put an electron here, it would go upwards because it's attracted towards the positive. If you were to put an electron here, it would go up. So here the field is going in the opposite direction. So the electric field would be going this way. Because if you were to put a positive test charge, it would go in would go in the opposite direction. If you were to put a positive test charge, it would follow the electric field. So here you've got the electric field. If you were to put positive charge, it would go in that field. However, we're talking about electrons. So the electrons are going that direction, so therefore the electric field is going that direction. All right. So now what happens when you change the current? So now the electric field is going to the right. Right, so can you see what this produces? This produces a curve. This produces a wave. So this produces, let me put this up. So let's just say that this is the maximum. What's going down, isn't it? So well, it doesn't matter because we will produce a maximum. So let's just say the maximum is, assuming that this is down, up, and then down, and then up. So it would okay. So because this gradually alternates, because of this alternating current, the electric field will change direction, and this produces a curve. Now this produces an electric field. Now do you remember what happens when you have a current? If you have a moving current in a wire, what else does it produce? It also produces a magnetic field. So it also produces a magnetic field. Right, so let me rub this out. Okay, so let's draw the current, the direction of the current and the magnetic field. All right, so let's just say that the current is the conventional current. So assuming that the conventional current is coming out, if you remember Chow, if it's going into the board, it's clockwise. If it's coming out, it's anti-clockwise. So assuming that you're looking down above, you can see that the current is coming out. So the magnetic field lines is clockwise. So it's going clockwise, it's going this way. So assuming that the conventional current is going up, so the conventional current is going up. Now if the conventional current is going up, the electric field is also up. So the electric field is also up. And the magnetic field, if you were to look at it head on, it would go to the left. So the magnetic field is to the left, so it's going this way. So what happens when the current decreases? As the current decreases, the electric field will go down. So now it is starting to go down a bit, and that will get weaker and weaker. The magnetic field is also getting weaker and weaker. So it's getting weaker. Now what happens when the current is going down? So now, instead of the conventional current coming out of the board, if you were looking down, what would happen if it's going down? The conventional current, or the electric field now, is going down. Now when it's going down, it means it's going so clockwise if it's going in, that means that's going out. Hold on, so that's out, that should be anti-clockwise. That should be anti-clockwise. So if it's anti-clockwise, it's going this way. Alright, so if it's anti-clockwise, that means the magnetic field is to the right. So this is getting weaker and weaker. It's getting... Okay, so now the conventional current is going down. That means the electric field is going down. So when you're looking up above, it looks like as though it's going into the board. And so that would be clockwise. So clockwise would now look like that is anti-clockwise, and it's clockwise this way. So now the electric field is to the, so now the magnetic field is to the left. All right, so can you see that because you've got current moving up, there's an electric field going up. If you were to take the conventional current as going up, so the electric field is going up. Now, because you've got a current, it also produces a magnetic field around this wire. It produces circular wires. So if you were, so here's the wire, and here you've got inside the current. It produces concentric magnetic field lines. All right, so because the electric field is going up, the magnetic field is to the left. But the stronger the electric field, the stronger the magnetic field. As it gets weaker and weaker, the electric field gets weaker, the magnetic field also gets weaker. However, because we want an alternating current, so alternating current means that it's going one direction and then it changes, it goes to the opposite direction. So now what happens when the conventional current goes down, the electric field is going down, and when the conventional current is going down, the magnetic field is to the left. What happens when that gets stronger? So as that gets stronger and stronger, that gets stronger and the magnetic field gets stronger as well. So can you see that there are two fields? You've got an electric field and a magnetic field. They join together. So if you were to draw a three-dimensional picture, so this one here, the one that's lying flat in that direction, will be the electric field, and the one that is perpendicular at right angles will be the magnetic field. So if we were to just, so here you have, so let's just say that this is the X and the Y. So the X and Y axis, and then you have the X and Z axis. So, and this is Z, and it's going this way. So because you've got changing electric field, you've got a changing magnetic field, and that is basically an electromagnetic wave. So when you have a changing potential, so for example, if you have plus, 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 and minus, 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 and then you gradually change to minus, 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 plus, 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 because the changing of the electric field, you're changing the magnetic field as well, and therefore that produces an electromagnetic wave.
Electromagnetic waves are time-varying electric and magnetic fields that travel through empty space or through insulating materials. So have you look at the diagram, you've got X, Y and Z axis, and you've got the electric field with E, and can you see that's in the XZ plane? So if you look at the X and the Z axis, that is where the electric field is, and the B field, the magnetic field, that is in the Y-axis and the Z-axis, and both are perpendicular to each other, and that is the diagram of an electromagnetic field. Alright, so when electric fields are accelerated, meaning that there's a force acting on it, for example, electromagnetic waves are produced. If we let an alternating current flow through a wire, for example an antenna, an EM wave is created. The frequency of the waves created is equal to the frequency of the alternating current. Now, our eyes are sensitive to visible light, and visible light is not absorbed by the atmosphere. Now, if you have a look at the list of the groupings of the EM waves, so you have radio waves, microwaves, infrared, visible, UV, X-rays and gamma. So the longest wavelength is near the radio wave, isn't it? So the radio wave have the longest wavelength, then it gets shorter and shorter, and the shortest is gamma. So the gamma rays have the shortest wavelength. Now, because the longest wavelength imply that there are less waves per second, that would imply that there is a low frequency. So the one that has the longest wavelength, radio waves, it also has the lowest frequency. And gamma rays, because the wavelengths are very short, it has a high frequency. Now the property of EM waves is that they travel at the speed of light. So it's 3 times 10 to the power of 8 meters per second. They can be reflected, they can be refracted, they can be diffracted, they can be polarized because they're transverse waves. Now the skin can absorb infrared radiation and food absorbs microwaves. The equation is V is equal to F times lambda.